This video, through a number of slides, explains the definition of a parallelogram and whether or not it has line symmetry, rotational symmetry, or both. The following slides will explain line symmetry, followed by rotational symmetry, and then the last one will talk about the properties that define a parallelogram. Line symmetry can be defined as a line, or an imaginary line perhaps, which can be drawn through a shape or an object, and everything to one side of that line will look exactly the same as everything on the other side of the line. So I've provided some examples here below because there are some shapes that may have no lines of symmetry, some that have one, and some that have more than one. So for example, the square has 4 lines of symmetry because there are 4 different ways we can fold it so that one half will match over the other half. An equilateral triangle will have 3 lines of symmetry as there are 3 ways we can fold it so it will match over itself. The rectangle only has 2. It's a common error for sometimes people to think that there is also a diagonal line of symmetry in a rectangle. The easiest way to check that this is not the case is actually just to get a rectangular piece of paper and fold it. Another example would be an isosceles triangle where 2 of the sides and 2 of the angles are the same. That has 1 line of symmetry. And you may notice the parallelogram there, that actually has no lines of symmetry. You may think that by drawing in 2 diagonals that we may be able to get a line of symmetry, but in fact that is not the case. However, for a rhombus is different to a parallelogram in that all of its sides are the same length. That does actually have 2 lines of symmetry. Rotational symmetry varies from line symmetry in that a shape is said to have rotational symmetry when it looks the same after it's been rotated or turned less than a full turn and it matches over itself. And the number of times that the shape matches over itself while you're doing the full rotation is called the order. So I'm not able to rotate these shapes here, but if you look at the link below, you can actually see some examples there of shapes rotating. But for example, the trapezium there, if we rotate that, it is not going to match over itself completely until we've done a complete 360-degree turn. So that doesn't have rotational symmetry. However, the square, that will match over itself 4 times by the time it gets back to doing a full turn. So we say that that has rotational symmetry of order 4. The pentagon, the regular pentagon that is shown below, that will have rotational symmetry of order 5, as it will match over itself 5 times in the process of doing one full rotation. The parallelogram, that will actually have rotational symmetry of order 2. Once it's completed a half turn, it will match over itself, and then when it's done the full turn, of course it will match over itself again. So rotational symmetry of order 2, as does a rectangle. The triangle, the equilateral triangle there, will have rotational symmetry of order 3. In this slide, we're going to discuss the definition of a parallelogram. So a parallelogram is a quadrilateral or a 4-sided 2-dimensional shape with straight sides where opposite sides are parallel. So these arrows here denote pairs of opposite parallel sides. Also, the opposite angles in a parallelogram will be equal. So, by definition, we are used to seeing a parallelogram that looks like that one there. However, if we think of the definition of a parallelogram, let's take the example of a square. A square has one set of parallel sides there, opposite parallel sides, another set of opposite parallel sides there, and its opposite angles, those 2 are the same, and this pair of opposite angles are also the same. So in fact, a square also fits the definition of a parallelogram. Let's look at the rectangle. Again, the opposite sides of the rectangle are parallel. So it has two pairs of opposite parallel sides. Let's have a look at the angles. These opposite angles are equal. These opposite angles are also equal. So like the square, the rectangle also fits the definition of being a parallelogram. The third shape here is the rhombus. Let's have a look if that also fits the definition. Well, these opposite sides are parallel, as are these opposite sides. So again, we have two sets of opposite parallel sides. This angle and its opposite angle are equal, and this angle and its opposite angle are also equal. So like the square and the rectangle, the rhombus also fits the definition of a parallelogram. So if we are considering the question that some of you will be considering later about rotational symmetry, line symmetry, and the parallelogram, remember, don't just consider the case of what we might consider to be our conventional or most common parallelogram, but it is also important to consider that the square, the rectangle, and the rhombus also fit the definition of a parallelogram.